But let's try this with our gyroscope. Okay? I don't want the string.
I thought I handed that to you.
I did not.
Not there.
Not there.
Okay, we're gonna have to improvise. It's always.
Okay. It's okay, I can do it with the hand. You think that'll work?
It's worth trying.
Worth a try. Okay. So we're going to first try this. We're going to start with the. We're going to suspend this just like I was suspending the ruler, off to the right, and it will appear to be rotating clockwise to me, such that the angular momentum is pointed that way. Okay?
So do you wrapping us up?
Yeah, good, right.
Okay. Go straight down.
So now the object appears to be rotating clockwise to me. Can we try this? We're going to try to suspend it. There we go. We're going to try to suspend it from this bungee cord. And
Got it?
yep, I got it. And we see that indeed it does process towards you due to the net torque, that when it's in this position, it points by the right hand rule towards you. Okay? No, yeah, we can stop it. We can start
Yeah,
again.
that's better.
So here's a question that came up on the checkpoint. And I like this question a lot because it's the only question I've seen that had a uniform distribution of the answers. So there were 4 answers. I think the distribution was 29.5, 29.5, 11, and 29.5 or something like that percent across the answers. So the question is now, I had that object rotating such that it looked like it was rotating clockwise to me. The initial angular momentum was pointed towards the door. If I rotate it the opposite direction, do you think that the gyroscope will precess if it's rotating in the opposite direction? Do you think the precession will be A, the same direction, or B, opposite direction? Okay. All right, let's see some answers. 1, 2, 3. Okay. Let's see a good healthy mix. So we'll give it a try. While Dave, you want to get that started up?
Yep.
Okay. While Dave's getting it started, I want to ask a question. If I start the gyroscope in the same position with the suspended point over here, the mass over here, what's the net torque acting on the object? Right? We still have the radius to where the force is acting, so I want this all the way.
Oh, the other one, right?
We'll try this now. So indeed it is processing the opposite direction. Right? But when it's right here, the net torque is still pointed towards you. Right? Okay. So the net torque is still pointed towards you. The only difference is that the initial angular momentum was pointed in the opposite direction. So the net torque represents a change, which means that if we have our initial angular momentum, a change in angular momentum, then a couple seconds later, the angular momentum is going to be pointing this way. And in order for that wheel to provide an angular momentum pointed this way, it has to process back this way. And when the torque was towards you, but the initial angular momentum was towards the door, then that meant that the object had to process this way in order to undergo a change in angular momentum towards you. Right? So indeed, if the initial angular momentum is in the opposite direction, then the precession will be in the opposite direction. Okay, so somebody asked an excellent question on the checkpoint yesterday. They said that, okay, this precession thing is pretty confusing. Is there another example of precession other than just a simple gyroscope? And yes, there is. There are lots of them. Anytime you have something rotating by itself, if you try to torque it, it will precess. But a classic example, and Dave really likes this example, is during World War I, was the first time air warfare was used, and the most popular plane and the most common plane was the World War I biplane, the Sopwith Camel. And this had, right in the front, it had a single propeller right in the middle. It would spin around. And then in order to turn the plane, you had a propeller here that would spin, then you had the plane body like this, and you had a wing and another wing like this. So you had angular momentum from this rotating propeller that was pointed either forward or backwards. I don't know which way it was rotating. And then you had a rudder on the back that would turn to turn the plane left or right. So this is an example where you have a big component of angular momentum, and you try to torque it in a direction that is perpendicular to the angular momentum. Right? So if we're trying to turn to the right or left, we're trying to apply a torque to the right or left here. And just like over here, we had the angular momentum, we applied a torque perpendicular to it, and it made the object result in a motion that had a change in angle perpendicular to both the torque and the angular momentum. When the Sopwith Camel tried to turn left or right, it would actually move up or down. And this is extremely counterintuitive, and it's extremely difficult to fly. And so the Sopwith Camel, being heavily used in warfare, wound up, I think, and this is a little bit of an urban legend, but it wound up resulting in the deaths of approximately as many training pilots as it did enemy pilots or enemy soldiers. So it killed as many people learning to fly the plane as it did in actual warfare, only because of the precession due to the gyroscope motion of the propeller. Right? If you're coming into land and you try to turn left and you actually go down, then you crash. Okay? Yes?
Well, why didn't I just like make the rudder go up and down? I know that side to side makes you go up and down.
Well, so that's the thing. Once you figure out how the controls work, then you can fly, and you can fly it very well. And it was a very successful plane, but it's extremely counterintuitive. Right? What they wound up doing is on the next generation of planes, they made two propellers. One spins this way, the other spins this way. And so there's net zero angular momentum. You can turn it however you like. Right? Okay. So these are some of the basic definitions of angular momentum. This here and this here. Newton's second law for rotational dynamics. But there are a lot of situations where we say that the net external torque acting on a system is 0, and in that case, the angular momentum must be conserved. Look at the system here. If it's being suspended by a string instead of my arm like this, there's a tension upwards, right? And there's a weight force downwards. And those are the only two forces acting on the gyroscope. So we have a tension upwards, and we have the wheel. We have a weight force downwards. These are vectors. And about any pivot point, the torque generated by those forces is equal to the distance from the pivot point cross product times the force itself. And so the torque must always be perpendicular to both the radius from the pivot axis to the point of where the force is acting. And it must be perpendicular to the force itself. So the torque is always perpendicular to the force. And so if all of our forces are up and down, we know for sure that we have no torque in the up and down direction. And we know for sure that angular momentum in the vertical direction must be conserved. In the situation where we started with the gyroscope, at the beginning, the angular momentum was absolutely 0. I'm going to ask you to predict the outcome of some of the demos. And I want you to answer the first couple based on these answers here. So we'll say A, speed up, which means that omega final is greater than omega initial. B is slow down. Oh no, B would be the same. Omega final is equal to omega initial. And C will be slow down. Omega final is less than omega initial. And so what we're going to do first is I'm going to hold these heavy weights in my hands, and Dave will get me spinning around on the stool, and then I'll pull the heavy weights inwards. Okay? And so what do you think will happen when I start to pull them inwards? Will I speed up? Maybe we should move away from the edge.
Let's think about that too.
Okay, so will I speed up? Will I slow down? Or will I stay the same? Speed up. Okay. And you can put your answer cards up with just A, B, and C. Okay. All right, we'll start out. Go ahead. Yep. Not that. Whoa. Whoa, slow down. Okay. So now I'm going to pull them inwards, and we'll see what happens. Okay. So did I speed up?
Yes.
Yes, I did.
Stop.
Yes. Okay. Okay. So you are indeed correct. When I bring the center of mass, or when I bring the masses closer to the axis of rotation, I am reducing the moment of inertia of the system of me and the stool and the masses. Right? Because my moment of inertia doesn't change very much, except for that my arms are extended further out. The majority of my mass is not in my arms. But those are heavy weights, and when I bring them in, I'm bringing a lot of weight closer to the center, so I'm reducing I. But there is no net external torque acting on the system, so angular momentum must remain constant, which means that as I goes down, angular velocity goes up. It must increase to maintain the same angular momentum. And this is how, of course, figure skaters do their twirls, where they start out with their arms wide out, and then they pull them in very quickly, spin around very fast, and extend them to land. Because if you landed with them pulled in, it would not be fun. And the opposite is true. At the end, when I wanted to stop, I had to let the weights back out so I could slow down. Okay, now this time, Dave is going to start me spinning with my arms extended without the weights. And then I'm going to come around and grab them from him. I'm going to grab them one at a time because I'm not coordinated enough to grab them both. But as I pick up the weight, what do you think will happen? Do you think I will speed up or slow down or stay the same? Okay. All right. Can we get started? What's that? Okay. All right, now. Wait. I'm going to do this. Switch hands. I speed up momentarily. And then I'm going to grab the other weight. So what happened when I grabbed the weights? Slow down, right? Okay, so I did slow down. And I slowed down for a good reason. First of all, I was increasing the moment of inertia. But also, when Dave was holding the mass still, I came around and I grabbed the mass. And I had to accelerate that mass up to the speed of my hand. Right? And that requires a force. And by Newton's third law, there's a equal and opposite force backwards on my hand. And that force backwards on my hand at a radius r from the center of rotation is a net torque acting on me. So that net torque acting on me from the mass indeed slows me down. Okay. All right, this time, Dave is going to get me spinning with the masses, and I'm going to drop them, okay? And hopefully not break the stage. Okay. So can you get? Let's get you going. Okay. So now, when I drop these, what do you think will happen? Will I speed up? Will I slow down, or will I stay the same? Yeah. Let me see your answers.
Lots of A's.
I can see the color. I can't read.
A couple B's.
Okay. Okay.
Bunch of A's, lots of A's. I think the A's have won.
Okay.
Yay, democracy.
So I'm going to drop them. Pay close attention. What happened? Did I stay the same?
Yeah.
Physics works.
Physics works. Yeah, I stayed the same. I should have spun for that long. Dramatic effect. Right?
Yeah, I was thinking you could ask the question before you got on the stage.
Okay. So I did stay the same. And I stayed the same because when I drop them, there's no net external torque. It doesn't take any force backwards or side to side for me to drop them. I just let go. If you recall, from early on, we said that the angular momentum of the whole system consists of the linear momentum of all the little parts of the system moving. And when I let go of the mass, if I'm spinning and I let go of the mass, I'm going to use this chalk instead because it's lighter. What happens is that it's not that the mass stops all of a sudden. It keeps moving in a parabola. It maintains its linear momentum which, whether I'm holding it or not, looks from the perspective of the central axis here as an angular momentum, right? An object moving in a straight line past this axis, but a distance away, is an angular momentum. Right? So angular momentum is conserved if I let go of that object. That's not a problem. And that doesn't slow me down at all. Now there's a reverse analogy. We showed you the example of me picking up the weights to begin with, intentionally to be confusing. The reverse analogy is if Dave, instead of holding the mass there and I pick it up, if Dave moves the mass by my hand at the right speed and then I pick it up, then I shouldn't slow down at all. We'll see if we can do this. I'm going to switch hands again. Right? There I didn't slow down. Okay. So, because when he was moving them by my hand at the right speed, they had the same linear momentum as if they were part of the system moving at the right angular momentum. Yes?
So even when it's moving the weight, is it still part of the system of you and the weight? Like even when you're not holding it? Or when you like drop the chalk,
Yeah.
it's like moving in parabola, is it still one system?
Yeah, you can consider it as one system. Once it hits the floor, then there's, then obviously that comes to a stop, but it's no longer able to exert a torque on me because it's sitting over there on the floor, right? But yes, you can consider that just like you would consider in a collision, you know, the two objects before the collision and after the collision are one object, are one system, where momentum is conserved. The same is true here. When things you know, come together and release, you can consider those as kind of collisions. So you can consider the total momentum of the whole system. Right? Yeah?
Well, if instead of dropping the weights, you like threw them in one direction or the other, would you accelerate or slow down?
Yes. Because then the weight would have angular momentum greater than as if it were just moving around. And I would have less. So that would be a form of collision. And just like we had this problem where, imagine you're stuck on the ice and you have to get off, you have to take off your shoes and throw them one direction. If you're spinning around and you want to spin faster or stop spinning, you could take off your shoes and throw them both, you know, provide a net torque by throwing them both in one direction. So if you're a figure skater that can't stop spinning around on a frictionless surface, you could indeed use the same trick. You take two objects, your shoes, and provide a net torque to make yourself stop spinning, right? By injecting mass in a way that provides a torque opposite to your direction of angular momentum. That's a good question. But yes, indeed you can. Okay. Okay, for the next couple of demos, I want you to answer according to the following scale. So A will be up, B will be down, C will be to the side, and D will be 0. Okay? And what we're going to do is we're going to combine the gyroscope with the spinning stool. Okay, and what we're going to do is Dave will get the gyroscope started, and then he will hand me the gyroscope so that I can hold it like this. It's oriented vertically. Okay, so why don't we go ahead and do that?
Do you care which way standing?
No. right now, what direction is the angular momentum of our system? Use your answer cards. Is it up,
Wheel
down,
spinning.
to the side,
Or
or 0? Right. The angular momentum, because the wheel is spinning towards you by the right-hand wheel, I'm not going to stick my thumb out into those spokes. The angular momentum is pointing towards Dave. It's to the side. Now I'm going to rotate 90 degrees. Okay? Okay? So now, what direction is the angular momentum of this system pointing? Let me see some answers when I come around again. Okay, I can't see very well, but you're
A's.
probably all wrong.
Some B's. I see some C's, couple C's, a D,
Okay.
one D. Any other D's?
Let me see.
Three D's.
Let me see those answers.
Just look at
Yeah, check the answers.
He's no right.
Yeah, mostly wrong. And this is why angular momentum is really counterintuitive. Right? And it's good. So when we started, the angular momentum was indeed to the side. It was pointing to the side. I'm sitting on this stool. What forces are acting on the system of me and the stool? Gravity. What direction does that point? What else? Normal force. What direction does that point? Upwards, right? So can there ever be any torque in the vertical direction? No. And what's my angular momentum in the vertical direction when I start? 0, right? So then when I torque it this way, and now, because there's a normal force on the floor, there can be torques in all these directions. But there's no torque in the vertical direction. So if I started with 0 angular momentum in the vertical direction, I end with 0 angular momentum in the vertical direction. So when I torque it this way, the wheel is obviously spinning sideways. So I don't know whether it's up or down, but the angular momentum from the wheel is up or down. I'm rotating this way, which means that my angular momentum is up or down. Actually, in this case, it's up. And those are the only things that are rotating. So because we know that the rotation of both objects has angular momentum in the vertical direction, we know that the angular momentum in all the other directions is 0. And because we know that there was no net torque in the vertical direction, we know that the angular momentum in the vertical direction is also 0. So the total angular momentum has to be 0. So the combined, so I spin around with the upwards angular momentum because the wheel has a downwards angular momentum. So it's the conservation of 0 angular momentum that gets me spinning around. Okay. So now we're going to do this demonstration again, not for any educational purposes, but mostly just for fun. But this time we're going to start with the wheel spinning. I'm going to hold it like this so that the wheel is spinning with an angular momentum that is upwards or downwards. Okay? And then what I'm going to do is I'm going to flip it over. Okay? I'm going to try to flip it over. Ready?
Flip it faster.
There you go.
Feel the burn.
There you go. Okay. As it slows down a bit, I'm going to go back the other way. No, I'm not. Okay.
You got some funky joints.
Yeah. Okay.
Ready?
Yeah, I'm done. Okay. That's incredibly hard to do. but it gets you spinning very, very fast. Okay, are there any questions about angular momentum? No? Okay. Then if not, I will see you on Wednesday